Potential energy example number 2. Let's consider a positively charged styrofoam sphere. Make it a nice green color. Positively charged. Attracting a negatively charged styrofoam sphere. Boom. They both have masses of 0.003 grams. That's a pretty small mass. Mass is equal to 0.003 grams, which is equal to 1, 2, 3, 4, 5, 6, 10 to the negative 6 kilograms. We want it in those SI units. Each of them are that mass. They had been rubbing against multiple objects in an old package. One ball came out with a charge of positive, that's the green one, 1.7 times 10 to the negative 7 coulombs. Due to missing electrons, ball number 2 came out with a charge of negative 2.1 times 10 to the negative 7 coulombs due to excess electrons. Those two will attract each other. They land 3.0 centimeters from each other. I'm going to say that's the distance from center to center to make our math a little easier later. That could have been the distance from edge to edge. I'm going to make it easy. So that's 3.0 centimeters, also known as 0.03 meters, also known as, more importantly, our initial. Assuming they are resting on a frictionless surface, how fast will they be moving when they hit each other? You may assume that due to their size, they collide when their centers are 0.05 meters from each other. So later on, they hit each other when their centers are our final 0.005 meters. So they're closer at the end. Make sure I really know what I'm talking about. It's asking a statement of how fast. Initially, they're not moving. And at the end, they're both moving. Okay, they're each moving. And because they have the same mass and they're experiencing the same forces, then they will be moving at the same speed at the end. All right. What's going on here? I'm going to do an energy interaction diagram because there's going to be a decrease in electric potential energy because initially they are a large distance from each other, and at the end they are much closer. And then there are two objects that are changing their kinetic energy from not moving to moving, we don't know how fast. So it's a speed up, and there's two masses that are doing that. So I have a little times 2 there. No, nothing else is affecting what's going on. Change in electric potential energy plus 2 times the change in kinetic energy of one of them is equal to 0. The change in electric potential energy is K Q1 Q2, 1 over R final minus 1 over R initial, plus 2 times 1/2 m v final squared minus v initial squared. V initial is 0 equals 0. Simplifying this, k q1 q2 1 over r final minus 1 over r initial is equal to, those 2's cancel, sorry, and that should have been a plus, not an equal sign. M v final squared equals 0. Solving for v final, I get v final squared is equal to, I'm going to take this whole thing to the other side, and when you move it to the other side, this term becomes positive and that term becomes negative. So that'll be k q1 q2 1 over r initial minus 1 over r final, then divide by the mass so the v final is alone. There we go. Let's plug in some numerals. V final will be equal to the square root of k, which is 9e9 approximately, q1, which I wrote down way up here. Q1 is going to be the positive number, 1.7 e negative 7. Q2 is a negative number, negative 2.1 e negative 7 coulombs, divided by the mass, which is 0.003 grams, or 10 to the negative 6 kilograms. And lastly, I need to get this R final minus R initial inverted in there. So the 1 over 0.03 minus 1 over 0.005. Putting all of this in my calculator. One of the reasons I like graphing calculators is you can see the entire equation like this when you plug it in. 9e9 times 1.7 e negative 7 times negative 2.1 e negative 7 divided by 10 to the negative 6. Enter. And then I'm going to multiply it by the parenthetical times, parentheses, the inverse of 0.03 minus the inverse of 0.005. All that, and don't forget the square root. And I get the final speed of each of them individually. It's going to be 231 meters per second. That's fast. That's like speed of sound. About half the speed of sound fast. Which means something really important. We omitted something that probably should have included, but we're not going to. These are styrofoam peanuts, just little things. And I said way up at the top that this is a closed system. In practice, you're going to have to worry about air resistance. Okay? I made a hint that we're trying to make this as user-friendly as possible, saying it's frictionless and stuff like that. But in order for these to not experience air resistance, is actually a very large assumption. So this answer is only true without air resistance. Having an air resistance consideration as well would be a much more difficult problem. And at a speed like this, 231 meters per second, air resistance would be important. So this is the fastest it could be. V final max. There we go. That is the fastest they can be moving due to their attraction to each other as they're coming together. This is the speed that would happen in a vacuum, for example. There we go.